So this is section 3 from chapter 8, graphing general rational functions, and there's a warning here that this is going to be tough for a lot of you, and we need to make sure that we're paying attention, make sure that you're trying to absorb as much as you can. I will go slow. I highly doubt that I will fit this into one video. We will see, but you really got to pay attention. There's things on here that I know you guys have struggled with early on. I know that there are certain things from section 2 that I think that you guys were starting to understand, but now we're taking it to the next level. So this is all graphing. It's still all graphing, but the steps that it takes to get to where we need to be, we just really need to make sure that we take this slow, one step at a time. Okay, so what we're going to start with is, let's just take a look at what's given to us here. We're graphing rational functions. This is very similar to what we were talking about in section 2, except now we're going to talk about how we can change the degrees of all of our equations. So before, it was always like a number over, something to the first degree. So like we saw things like, 3 over 3x minus 1. Okay, well now we're talking about raising the degree. So we may have squareds, we may have third power. For the most part, we're not going to get any higher than squared, especially in this section. But the idea is we can now have quadratics, and we can have cubic functions in some cases, things like that. So it is going to get a little bit more difficult with that respect. It's just a little bit different, but some of the ideas are still the same. So what we're going to do is the first thing we're going to look for is we're going to look for x-intercepts. Well, if you recall, when we have a fraction, it doesn't matter what our fraction is. If I gave you y equals x minus 2 over 3, an x-intercept is always going to be where y is equal to 0. So in the case of a fraction or a rational function like what we're dealing with, if the top is equal to 0, that will give you an x-intercept. So wherever the top is equal to 0, so you can write that down, top equal to 0. Because whenever the top is equal to 0, that will give us an x-intercept. The second thing is the graph has a vertical asymptote at each real 0 of q of x. That's the same thing as we did yesterday, whenever this bottom is 0. So in this case right here, there wouldn't be one because the bottom is never 0 there. But, okay, so asymptotes are going to be the same thing as before. It's when the bottom equals 0. Okay? And then the last part, this is the part that's different. So yesterday we talked about if we had a function that looked like this, we had x minus 2x plus 3, the horizontal asymptote would be the ratio of the beginning. Okay, so 1 over 1, so therefore horizontal asymptote on this one would be y equals 1. And that is still true. That is what you see here. Okay? Jumbled in all these letters, these are basically saying the degree. M and N is the degree. That's the power, the leading power of each of the functions. So here are our little rules that we have. If the top is greater than the bottom, if the top is less than the bottom, if the top is less than the bottom, so if M is less than N, in other words, if the power on top is less than the power on the bottom, we will automatically get y equals 0 as our horizontal asymptote. Okay, so this is degree of top is less than the bottom, and it's degree of the bottom. Okay, this middle one is when the degrees are equal. That's what we did yesterday. So if you had a squared on top and a squared on the bottom, then you're going to go to your leading coefficient, and it would be a fraction of those. Okay, so just like yesterday, 1 over 1 or 5 over 2, depending on what it is. So degrees are equal. And then the bottom one is just reverse of up here. So this is if the degree on the top is greater than the bottom. So that's all these letters are representing, is the degree. And if that's the case, then it will have no horizontal asymptote, so we won't have one at all. So literally what I want you guys to do, and what I want you to think about as we go through these problems, is let's take them one step at a time. We're going to first see if there's any x-intercepts. Then we're going to find our vertical asymptotes. and then we're going to see if we have any horizontal asymptotes. Then what we will do is we will plot everything that we know from these three things, and then we're just simply going to make a table. So if we take it one step at a time, it might not be too bad for you guys, but there are going to be certain things that I know you guys struggle with. So let's look at this first example. We have y equals 3 over x squared plus 2. First of all, the numerator has no zeros. There's no x, there's no variable on the top. So therefore, there's no zeros on the top. Okay, so therefore, there are no x-intercepts. Okay, so also, if you look at the bottom, x squared plus 2. Now, this is something that we've really struggled with. If I wanted to take x squared plus 2 and set it equal to 0, you would end up with x squared equals negative 2. Well, if you know anything about squareds, a squared can never equal a negative. Therefore, this will never be equal to 0, so therefore there is no vertical asymptotes. Okay, so there's no vertical asymptotes, there's no x-intercepts. Okay, now we look at the degree. The degree of the top is 0, and that is less than the degree of the bottom, which is 2. So because it's less, okay, we have a horizontal asymptote of just y equals 0. That was the first little property we set up here. If the degree of the top is less than the bottom, then it's y equals 0. Okay, we're not going to worry about the domain and the range yet, so let's just go through and do exactly what we're going to do here. So we have no x-intercepts, we have no vertical asymptotes. The only thing that we have is we have a horizontal asymptote at y equals 0. So I'm going to do a line there. Okay, so there's our horizontal asymptote. Okay, seems pretty straightforward so far. So now what we're going to do is we are going to actually create a table of values. So just like what we did yesterday, we need values. Now, for this, we have no vertical asymptote, so it really doesn't matter what values you pick. I would just pick something that are to the left of the x-axis, or to the left of the y-axis, and then to the right. I've picked 5 values. I'm going -3. And these are just random. I mean, I just picked -3 and -1, and then 0, and then 1, and then 3. There's no reason why I picked those. It was just I wanted to make sure we got far enough to the left and far enough to the right and something in the middle. And here's what I got when I plugged these in. Again, I'm just plugging them into here. Okay? So here's what I got. Just to save time, I got 3 over 11. I got -1, comma 1. I got 0, comma 1.5. And I got 1, comma 1. And then I got 3 over 11. So then all I do is go through and I plot these. So again, I know this graph is pretty small, but just kind of hang with me the best that you can. So -3, and there's going to be a dot right here. And then we go -1, there's going to be a dot right at 1. And then we have a dot at 1.5, and then another dot at 1, and then another dot really close to the x-axis here. So again, you can't see this without a graphing calculator, and this is what I'm going to want you guys to do, is you're going to want to, when you're at school, you're going to want to put these into the graphing calculator to see what the general shape is. So that way you can see how the curve goes. But you can kind of see this is a curve that approaches the asymptote. It goes up into this like little mini hill and then comes back down and approaches the asymptote again. Okay, so that's what our graph looks like. And honestly, when you see graphs like this, you know, a degree 0 and then a squared on the bottom, this is pretty much what your graphs are going to look like. It should look like almost like this little anthill. Okay, so now let's talk about the domain. The domain is your x values. We talked about this earlier. That means all of our x values. We go all the way to the left, we go all the way to the right. There's no restrictions, so therefore our domain is just all real numbers. There's no errors, there's no undefineds. You could put any x value in here and it would be fine. That's why it's all real numbers. Now for our range are our possible y values. We got to be careful here, and this is where I think you guys are going to struggle a little bit. So here, the idea is that we are not going anything less than 0. We're actually staying above 0. So 0 is the lowest value that we go to, and 0 is going to be less than y, because that means y is bigger than 0. But also, we cap. We top out right here. We don't go any higher than this. That's as high as our y value goes, which is at 1.5. So therefore, y has to be less than 1.5. In a sense, it can be equal to as well. So make sure we don't forget that equal sign. So in a sense, we're saying that y is going to be in between 0 and 1.5, which makes sense. When you look at the graph, your y value is in between 0 and it actually touches 1.5. That's why we have less than or equal to there. Okay? So what I want you to do is, if you, hopefully this made sense for this first example. Like I said, this is going to take a little bit of time. What I want you to do is go ahead and try and do this one on your own, and then hit play when you're ready. All right, so hopefully this is the graph that you got. Real quickly, we had no x-intercepts, no vertical asymptotes again. Our horizontal asymptote was y equals 0 because the degree on the top was less than the degree on the bottom. I plotted our points with our asymptote. This is what the graph should look like. Very, very similar to the graph that we just did. And you see now the domain of this is still all real numbers, just like the domain was all real numbers here. You can put any x value in here and it doesn't matter. Okay, it goes all the way to the left, all the way to the right. That's why it's all real numbers. And our range, which is different, it's our y values. Our y values start at 0. They cannot equal 0, so it's just less than. And it goes all the way up to 3, and it can be 3, so that's why it's less than or equal to 3. So the range is 0 is less than y, which is less than or equal to 3. In other words, y is in between 0 and 3. It can equal 3, it cannot equal 0. Okay, so go ahead and this is going to be it for this video. Then part 2 is going to be example 2. So go to part 2.